And when I think about my overview, one of the things that we've done is we've talked about atomic structure. And I said that we spent a significant amount of time on that because, I mean, we just need the language. Without the language, we can't even communicate. And now what I want to do here is I want to look at the properties of atoms. Okay, so now I want to start looking at the properties of atoms. And there's going to be, I could think of really 4 things. I think there's 4, there might be 3. And ultimately what we want to do in the properties of atoms is we want to talk about sort of like the size, quantity, and age of atoms. I think that's definitely one of the topics. In fact, maybe I should list them just so that I have them clear in my head as I lecture. So this will be the first one. And I think we should talk about the forces within the atom. Because deeply connected with the forces within the atom is a lot of people see the atom as being empty. And that's a really big misconception. And we're going to find that the electrical force of the nucleus is immensely, immensely strong. And then from here, we should talk about the models of atoms. And there's 2 major models. One is definitely Rutherford's model. It was Rutherford that put forward the planetary model of the atom. And like I said, probably a zillion times up to this point, he knew in 1910, after the discovery of the nucleus, that it was a wrong model. But it's the image that the vast majority of people today actually see. And then what we'll do here is that we'll hit almost a quantum mechanical model. And I would call that the quantum atom. And the quantum atom that we're talking about is, we're mostly going to look at what's called the Bohr model, but the Bohr model is really not a quantum model because the quantum model's too complicated to go through in this course. But we'll hit some of the highlights that really, really show what it is. Okay, so let's start then. So I want to look at these properties of atoms. And so let's talk about the size and quantity and the age of atoms. Okay, so the first thing that I'm going to do is I'm going to go after the size and quantity of atoms. So you've already heard me say that the pictures that I draw of the atom are vastly incorrect. They really, really are vastly incorrect. So I'm going to draw a picture of a nucleus, which is incorrect. I'm going to draw a picture of an atom, which is really incorrect too. But there's no other way to really talk about it, so that's what we have to deal with. So the nucleus is extremely tiny. And it's hard to comprehend just how tiny this thing is. So a lot of the times you've been seeing us draw images of the nucleus where, from time to time, you'll see me come in and I go, okay, here's some protons. Okay, here's some neutrons. And it kind of looks like this here. It turns out that that's not a very good working model. So we draw a picture and we just kind of symbolize with this. And so what we'll do here is that we then come in and just say, okay, this size here is the diameter of the nucleus here. Actually, I'm going to move this over here and just say, yeah, that's the diameter right there. Then we ask the question, what is the size of the nucleus? Well, it's 10 to the negative 15 meters. And you look at that number and you got to ask yourself, what does that even mean? I can't comprehend what this means. But if you were to actually kind of write this, you'd go 1, 2, 3, 3, 1, 2, 3, 1, 2, 3, 1, 2, 1 meters. That's what 10 to the negative 15 means, right? It's pretty damn tiny. I have no comprehension what that number actually means. And then we could say the same thing about the atom. We could say that the atom is, what is that? The atom is 100,000 times larger than the nucleus, but still tiny. So when I think about what we're seeing here, so what we find here is that that nucleus is a really, really tiny thing. And then we'll say that somewhere in here is the electron. We don't know where, we just know that it's contained by the electrical force here. So what we'll say here is that this thing here is the electron or electrons. This thing here is the nucleus. So when I go and I look at the diameter of this guy right here, right? Again, this is the diameter. And then we ask the question, how big is that? Well, if you look at hydrogen, hydrogen's one of the biggest atoms because of the way it spreads out. When you look at it, well, it's really 10 to the negative 10 meters, and it's most common to actually write it in nanometers like this. So it's 1/10 of a nanometer. But again, what is that number? Well, 10 to the negative 10 is tiny, right? So we got to go 1, 2, 3, 1, 2, 3, 1, 2, 3. Then we go 0, 1 meters. So we're throwing around these numbers and we're asking, well, that's the size of it. Well, of course, we can't just throw these numbers around because they're meaningless. I mean, so maybe a better way to answer this question, how small, is that we should say that since these numbers are meaningless, and what I mean by meaningless, we have no physical grasp of what they mean, right? One cannot comprehend their meanings. So therefore, what we do here is that we give analogies to get some feel. So it's common to give analogies. So here's some of my favorite ones. There's lots of them. Okay. I'll give you like 3 or 4 just so you get a sense of that. So the first one that I want to do is that if you compare the size of an atom to an apple, we would expect that there'd be a lot of atoms in an apple. The equivalent statement, so this would be an equivalent comparison to, so then the same comparison is an apple to the size of the earth. Now, I think everybody can comprehend that an apple is nothing but a speck compared to the size of the earth, right? Nothing but a speck. So, yeah, that means that the atom is quite small. And then to even another one that really kind of really sends this thing home is this, that the number of atoms to fill up the earth, fill up the apple. Again, we have that exact same equivalent comparison. This is also equal to the number of apples to fill up the earth. And when you think about filling up the earth with apples, that is just a staggering quantity of atoms in an apple. It's just incomprehensible. That's what I mean by when we look at these numbers, they're meaningless. But when we start talking about the size and quantity of atoms and things, it starts to give us an image that there's a lot of atoms. So these two statements are clearly state that atoms are numerous and tiny, right? So these clearly show that atoms are tiny and numerous. So what we find here is that we have something called a mole that describes the number of the quantity of atoms. So there is a scientific quantity called a mole that tells us the quantity of atoms. And that number associated with the mole is something called Avogadro's number. So if I look at Avogadro's number, I believe that might be spelled incorrectly. So what this does here is it tells us about quantities of atoms. And this number is really 6 times 10 to the 23. And what that really tells us is it tells us the number of atoms in a quantity called a mole. And what you find here is that we can approximate this to 10 to the 24. So just this number, 10 to the 24, is how we describe the number of atoms in a quantity. So it looks something, I mean, again, this number is incomprehensible. If this is 10 to the 24, and this is 10 to the negative 15 or 10 to the 15, these numbers are just unbelievable. And again, I could be quite terse in writing this out, but you're getting a sense of what I'm talking about here, right? So it has 24 zeros behind it. So how do we use Avogadro's number? The way we use Avogadro's number is that it's associated with the mole and Avogadro's number together. They're really like inseparable. So this number tells one how many atoms, or we could talk about molecules too. We could talk about anything, are in a substance. So to give you an example here, the first example, one of the examples is that let's think about water. Water is H2O. So now if I wanted to look at a water molecule, we can see here is that the mass of water, maybe I should say the mass of a water molecule, this is equal to, of course, 1 oxygen plus 2 hydrogens. So if we look up their masses, we see here is that this is 16 grams per mole. And then this guy is 2 times 1 gram per mole. And when you add that, this is 18 grams of water in 1 mole. Now remember, 1 mole has 10 to the 24 molecules. Now 18 grams, I'll tell you this. If I remember correctly, 18 grams is about an ounce of water. You know, I should have calculated it. I didn't. That's my bad. We could Google it, I guess. But 18 grams of water is about an ounce. It could be a little bit more. And so here's the question here. In 18 grams of water, right? So in 18 grams of water, there are 10 to the 24 water molecules. And that's where I want to go. What does this mean? Does 10 to the 24 mean? It is such an enormous number. It's a joke. It really is a joke, because check out these other two comparisons, okay? Look at this comparison. So if I look at this comparison, if one was to collect, right, all the drops of water in all the lakes and rivers of the world, 10 to the 24 is still larger. Think about that. If you collect all the water drops in all the lakes and rivers in the world, there are more water molecules in about an ounce of water than there is drops in all of those. That is insane, right? And here's another one. If one was to collect all the leaves on every bush / tree in the world, 10 to the 24 is still larger. Think about how amazingly strong that image is. Collecting every leaf from every bush and tree, and still there are more water molecules in 18 grams of water than there are leaves in every bush and tree in the world. That's what 10 to the 24 means. It's a number that's incomprehensible. But I think we should leave you with two more images on the size of the atom. So let's look at two more images on the size of the atom. So here's what I think I understand. So here's two more analogies. Okay. One, I want to talk about a golf hole. So as far as I know, we have a golf ball that we're going to hit, right? So I could imagine that this is the golf ball. And if you look at the longest golf hole that you might be able to find, it's typically about, I think I Googled it, and it's like 1,600 feet. It's about a third of a mile. So then that means here is that over here, you have a golf hole or a golf cup or a cup. So when you compare this thing, just to give you a sense of distance, and I'll come back to this number a little bit later, I could then say that the electron is the golf ball and the nucleus is the golf hole. And so if I compare this number then is about 1,600 feet, which is about a third of a mile. So when we think about this thing here, we could say that the golf ball is pretty far away from the golf hole here. And that's one comparison that we could think about in terms of what the atom is. And then what a lot of times people say here is that in here is empty space. That's what some textbooks claim. I strongly disagree with that, but that's one image. So you would see here that the electron is pretty far away from the nucleus, just from that image. And the other one here, which I thought was which I think was an interesting one, the largest possible church. Now, the largest church I've ever been to was the National Cathedral in Washington, D.C. And when you look at this church, I'm just going to tell you, it is gigantic. I mean, it's mind-boggling. The height of this thing, the width of this thing is just insane. So to get a sense of, again, the size of the atom, here we just talked about the distance between the electron and the nucleus being quite far when you're considering the size of the golf ball and the golf cup. But if you wanted to think in terms of volume, what you should think about here is that imagine right here at the center of this massive, massive church, you put this little tiny flea. And that flea would then correspond to the nucleus. Very, 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 very tiny. And then what you find here is that off over here to the edges of the cathedral, right? So right here, we're talking about the outer walls here. This thing corresponds to the location of the electrons. So once again, what you're finding here is that in between these guys, it's really devoid of massive objects. And they say, oh yeah, this is empty space here. But I think the cathedral one is the best, especially if you've been at the National Cathedral. It is staggeringly large. It's kind of shocking to me, at least.